Hey y'all, today I'm continuing the Calculus 1 series. We're moving on to applications of differentiation, and we're going to be talking about maximum and minimum values. So, first of all, absolute and local maxima. So, for absolute, basically, an absolute maximum or minimum is the greatest or smallest value of the function on an interval. So that could include one of the endpoints, or it could include like a place where we see sort of a hump and it's the top of the hump or the bottom of the hump, right? Local maxima and minima, those are going to be the places where just near the point, it's the biggest or smallest value. So let's see this in action. I think it'll make a little more sense on a graph. So basically, the endpoint of the interval that we have graphed is right here, right? And it's clearly the smallest value in this whole function on this interval. And so this is going to be an absolute minimum. All right, what about this value right here? So it's not the biggest value in the whole interval, but it is the biggest value near it. And so this is going to be a local maximum. Okay, this value right here, this is going to be a local minimum because it's the smallest value in the area around it. Okay, this value, so it is the largest value in the area around it, so it is a local max, but it's also the largest value on the whole interval, so it's also absolute. So this is both a local and an absolute maximum. Notice between these two, this is both local and absolute. This is just absolute. It's not a local minimum because it's just an endpoint, right? We don't know what's happening on the other side of here. We don't care. All we care about is that on this interval, it's the smallest value. So it's just absolute. And then this here, again, around it, it's the smallest value. So this is going to be a local minimum. And this endpoint, it's not local because it's an endpoint. We don't know what's happening over here. And then it's not absolute either as a maximum because this is bigger, right? So this is just not a maximum at all. Local or absolute, it's nothing. All right, so this is the extreme value theorem. So this theorem states that if we have a continuous function on a closed interval, then on that interval, the function's going to have an absolute maximum and an absolute minimum on that interval. So looking at this function, that kind of makes sense, right? We're going to have, at the very least, we'll have some point that's the biggest in the interval, whether it's at an endpoint or whether it's somewhere within the interval, and same with the minimum. Next is Fermat's theorem. So it says that if f has a local maximum or minimum at a value, then either the derivative of that value, the derivative at that value doesn't exist or it's zero. Now, let's look back up at here. So this is talking about local maxima, right? So at this point, where we have a local maximum, if we were to draw a tangent line here, the slope of it is 0. And so the derivative at that point is 0. Now looking at this, it's a sharp corner, and at sharp corners, the function's not differentiable. So here, the derivative doesn't exist. This is also, as well as being an absolute maximum, it's a local maximum, and the tangent line looks like this. The slope is 0. And then here, tangent line looks like this. Its slope is 0. So looking at the graph, this definitely makes a lot of sense. So a critical point of a function is going to be a number in the domain where either the derivative at that point is 0 or it doesn't exist. And so critical points are places where we could have a local maximum or minimum. In fact, all local maxima occur at critical points. Okay. Finally, we have a method for finding absolute maxima of a continuous function on a closed interval. So basically, our first step is just to find the critical points of the function in the open interval, right? So not including the endpoints. Next, we find the values of f at these critical points, as well as the values of f at the endpoints of the interval. we compare the values of f at the critical points and at the endpoints. The biggest one is the absolute maximum, and the smallest is the absolute minimum. Okay, so we're going to move on to an example. So basically, we're given a function and an interval, and we want to find the absolute maxima of the function on that interval. So the first step is to find the critical points of the function on the interval. To do that, we're finding the places where the derivative either is 0 or does not exist. So we have to actually find the derivative. Here, the derivative is 3x squared plus 6x. So that is going to exist everywhere, right? It's a polynomial. So we just set it equal to 0 and solve for the places where it's equal to 0. So we can pull out an x. And so we're going to get x equals 0 and x equals -2. So first, we could just plug those critical points into the function. So f of 0 is going to be 0 cubed plus 3 times 0 squared plus 6, which is 6. F of -2 is going to be -2 cubed plus 3 times -2 squared plus 6, which is -8 plus 12 plus 6. And so that is going to come out to 10. Next, we plug the endpoints of the interval into the function. So our left endpoint is -4. We plug that in. -4 cubed plus 3 times -4 squared plus 6. That is going to give us, let's see, -64 plus 48 plus 6. So 48 plus 6 is going to be 54. So then 54 minus 64 is going to give us -10. Now we plug in the right endpoint of the interval, which is 2. So we have 2 cubed plus 3 times 2 squared plus 6, which is 8 plus 12 plus 6. And so that is going to give us, let's see, that'll give us 26. So the biggest value we got is 26, and the smallest is -10. So 26 is going to be our absolute maximum, and -10 is going to be our absolute minimum. Now notice that both of these are at the endpoints, and so they are not going to be local maxima, just absolute. All right, if you enjoyed this video, please like and subscribe, and I'll see y'all next time.